So, welcome to morning session of the conference. So, today we have Professor Toshiyuki Kobayashi. He will be speaking on Harishchandra's admissibility theorem and beyond. So, thank you.
So, thank you very much. First of all, I'd like to express my heartfelt thanks to the organizers, in particular Apramayo and Dipendra, for their enormous effort to bring me to Harishchandra Institute in India. So thank you very much. So I'm very happy to meet my old friends, and in particular Indian friends, and also new people here. Thank you very much. So it's a great honor to be invited for this centennial conference of Harishchandra. Unfortunately, I didn't have an opportunity to meet him because he passed away, unfortunately, exactly around the time when I entered the undergraduate math department. However, in this talk, I'd like to emphasize some of his pioneering ideas in his achievements, and present some of the continuing outgrowths of his ideas in broader and different contexts. So, so in this talk, I plan to organize in that way. The first three topics about restriction problem to the subgroups. And then the last topic is different disciplines that, but still connected. We discuss about spectral analysis on locally Schur-Riemannian homogeneous spaces. But we shall see that this general result of the branching problems gives a new method to attack these questions. So this is my plan of this talk. So let me start with recalling Harishchandra's celebrated admissible restrictions. So this celebrated Harishchandra admissive theorems we recall now. G is a real reductive linear Lie group, and K are maximal compact subgroups. And then this admissive theorem later became foundations of algebraic approach of Gay-K modules, so-called Harishchandra modules. But not only that, for example, gives some proof that reductive group is type 1 in the sense of the von Neumann algebra. And this statement says that any irreducible unitary representations of real reductive groups, then each K types appears at most finitely many times. And this is irreducible unitary representations. And but now we use the following usual terminologies that are representations of pi. And here that as in the Bilget talks, that I use capital pi for representation of the larger groups, and then lowercase letter pi for representation of the subgroups, if we are thinking of the restrictions to subgroups. And so our representation pi is said to be admissible, and for our later terminology, we shall call this is a K admissible, because we want to change subgroups. If each K types appears finitely many times, as in these conditions. So the two features. One is that they compose discretely, and this is obvious when the subgroup is compact, and then finite multiplicity properties. And also we want to discuss for non-unitary representations, so including non-unitary cases. So let us fix some topology for continuous representations. And we shall adopt in this talk so-called Kastelman-Wallach globalizations. So let MZ be the category of smooth admissive representations finite length with moderate growth. So this is defined on fresh spaces. And so there's a natural equivalence of categories between MZ and high-Schindler modules, so finitely generated GK modules. And we denote by IL-Z the irreducible objects. Then there's an injective morphism from unitary dual to this irreducible representations, which is not necessarily unitary, by taking smooth vectors. Now, considering the multiplicities, we have to be careful when we deal with infinite dimensional representations, because we have to consider multiplicity either from small representations to large one, or large one to small one, and also depend on the topology. But we fix in this talk that by multiplicity we mean the dimensions of symmetry breaking operators, namely the dimension of the space of continuous intertwining operator from the representation of large groups to a representation of smaller groups, sometimes referred to as symmetry breaking operators. Okay, so this is the definition of the multiplicity. Now, our interest is to the how the representations, reduced representation of the reductive group behaves when it is restricted to the reductive subgroups. But as a first step, since we are looking at non-compact reductive subgroups, we can take compactable maximal compact subgroups by Mostow. And then first, we highlight the restriction from the left upper corner to the right lower corner, namely restriction from Z to K prime. Now we focus first on this. And then here's the theorems. We consider K prime is not necessarily maximal compact subgroups. It's compact subgroups. So we may assume that it is contained in K. Then we count the multiplicity of the restriction from representation Z to K prime, not K, K prime. And then the first conditions is that each multiplicity of K prime type occurs at most finitely many. So this is the conditions on the pair of representation pi and K prime. And the second condition is the criterion for when this happens. Namely, this is a cone defined by representations, and this is another cone defined by subgroup K prime. And if the intersection of the two cones is trivial, if and only if multiplicity is finite, restricted to K prime. To be more precise, this closed cone is a closed cone in the compact Cartan subalgebras, durable it, is an asymptotic K support. So this is defined by the asymptotic cone of all the highest weights of K types that appears in pi. And then there is only finitely many possibilities of the asymptotic K support for admissible representation K pi. So this is a closed cone defined by representations. And the second one is a closed cone defined in the same space, but defined by subgroup K prime. So we consider the Hamiltonian actions of the cotangent bundle of K mod K prime. And then we consider a moment set map. And then the image of the momentum set to this compact Cartan dual of the compact Cartan subalgebra is denoted by this set. And then the intersection is trivial of these two cones if and only if the finite multiplicity property holds. Stupid remark is that when K prime itself is a maximal compact subgroups, then the second conditions, so we look at these ones, and then this is at one point, and so the momentum set is trivial. And so this is 0, and so this condition is automatically satisfied. So in this case, this says that pi is, in the usual sense, admissible. But we don't give any proof because the definitions of this Z, we already assume the admissibility same. So this is just a remark. Okay. Now, the motivations of this is that, as we said, that we want to understand the restriction from Z to Z prime. So let us fix some terminologies. So suppose that pi is an irreducible unitary representation of z, and we restrict it to z prime. Then, as we mentioned, that reductible Lie groups is of type 1 in the sense of the von Neumann algebras, and so any irreducible unitary representations can be decomposed essentially in a unique way. And usually it has a continuous spectrum, but we focus in the special case where there is no continuous spectrum. So, namely, when the restrictions decompose discretely. And moreover, we consider the case when each multiplicity is finite. So this is not all less, but we call, if this satisfied, namely discretely decomposable and with finite multiplicity, we say that the restrictions is z prime admissible. So in this sense, that Harish-Chandler's admissible theorem, if we use this terminologies, means that any irreducible unitary representations is K admissible in our terminology. But we want to use this terminology for non-compact reductive subgroups. Then the motivations of this theorem is that we want to understand the restriction here, but we use the knowledge from the restriction to here or equivalent to the restriction here. So this is the theorem. And then what we can say from this theorem is the following. Suppose that this pi and z prime satisfies one of the equivalent conditions, so therefore any both of conditions is satisfied. Then the restrictions to non-compact z prime is z prime admissible. Namely, the restrictions to this non-compact subgroups decomposes discretely with finite multiplicity. And the converse is true, for example, if pi is Harish-Chandler's discrete representations. So classical examples that this happens include the following cases. For example, if we think of the theta correspondence, and we take, in this case, we consider metaphoric representations and consider oscillator representations. And let Z prime be compact dual pairs. And suppose that, so this means that Z1 and Z2 are centralizers of the other. And suppose that one of Z1 or Z2 is compact, then this is referred to as compact dual pairs. So in this case, the restriction from Z to Z prime decompose discretely and multiplicity freely. So this is a classical example of admissible restrictions. Another classical example includes a tensor product of two holomorphic representations. And so tensor product of any two holomorphic representations, a little bit more generally unitary highest modules, decompose discretely, and each multiplicity is finite. So this is admissible restrictions. And actually, by using the more recent theory of visible actions on complex manifolds, that we can control the multiplicities. And so in this case, we have a uniformly bounded multiplicities. And this upper bound is also controllable. Okay, so this is a classical example. And this the criterions tells us that there are more examples. So namely, this gives a list of family of triples, irreducible unitary representations, and a pair of reductive groups, for which the restrictions is Z prime admissible, namely no continuous spectrum and each multiplicity is finite. And the classification results include, for example, in the case when Z and Z prime are reductive symmetric pairs, and then, for example, if pi is a Harish-Chandler's discrete representations, or more generally, it is Zuckerman globalizations of the Zuckerman's derived functor modules that appeared in the lectures of yesterday by Jeff. And so then in this case, the triple is completely classified by using the criterions that I discussed. And also, in the case of the symmetric pairs, and also when pi is minimal representations, also we can tell in which case it is admissible. And also, the tensor product case, that without any assumptions on pi 1 and pi 2, that we give a classifications when this is admissible, namely no continuous spectrum, and finite multiplicities. And these three cases are restrictions with respect to the reductive symmetric pairs. But also there are some other, further results for non-symmetric pairs. For example, Duflo, Galina, and Vargas classified when the restriction to SL2R is discrete decomposer with finite multiplicity, where pi is a high-standard discrete representations. Here, we note that there are finitely many embedding of SL2R or PSL2R into Z up to conjugations. And then they classified in what kind of embedding that high-standard discrete representations is decomposed discretely and with finite multiplicities. Okay, so these are some classification results. But so these are based on the criterion that I discussed by by representative theoretic invariance. But we shall see that completely different stations that from some geometry connected with locally pseudo-Riemannian symmetric spaces that we give a family of triples that are admissible restrictions. And this will be discussed at the end of this talk. Okay. So this is some topics arising from high-standard admissible theorem. Okay, now let us go on the second topic. So we have given criteria, necessary and sufficient conditions of admissible restrictions, and also explain some classification results. But in general, that assumptions without continuous spectrum is too strong. So in most cases, the decomposition may have a continuous spectrum. And so we may forget the first conditions, and then we may get a broader setting with finite multiplicity restrictions. And then this is the topic of the second topic. But also, we may consider stronger assumptions that not only individual finiteness, but also we may ask ourselves when the multiplicity is uniformly bounded. In such a case that we may expect a detailed analysis of the branching problem. And so we want to understand, forgetting this discreteness of the equations, we want to focus on the multiplicities. So let us consider again the symmetric pairs. And here are the observations that we compare restrictions to maximal compact subgroups like high-standard case, and the restrictions to another real form of the same complexifications. And then we compare. Then in the former case, that we have already seen that any irreducible unity representations and any k types the multiplicity is finite. So this is High-Chandler's original admissibility theorem. But if we consider not ON but OPQ, P plus Q equal N, then it turns out that the restriction usually contains continuous spectrum, but more than that, the multiplicity often becomes infinite. So this means that control of the finite multiplicity is not controlled by complexified object. So this is an observations. Okay. Now let us give some terminologies, usual terminologies. So suppose that XC is a connected complex manifold acted by complex reductive groups. And XC is called spherical if Borel subgroup of B, Z, has an open orbit in XC. And analogous notions is defined for the real setting that we say, suppose that connected smooth manifold is acted by real reductive Lie groups. And we say X is real spherical if a minimal Parabolic subgroup P has an open orbit in X. And I call this, I use this terminology when in search of a broader framework in the late 80s for global analysis on homogeneous space than the usual case at that time. For example, analysis on group manifold by Hashchandras, and also analysis on reductive symmetric space by Oshima and others. Okay, so this is the definitions of spherical and real spherical. And so here's a relation between. So for example, if Z mod H is a reductive symmetric space, then its compressification is spherical. And this is a restatement of the theorem of the Joe-Wolf. And if we take any real form spherical space, then this is real spherical. But the converse statement is not true. So we are using not a Borel but minimal parabolic. And so compressifications of real spherical space is not necessarily spherical. So this is the remark. And also there's small difference between spherical space and symmetric space in the reductive case. Okay, and we have used the existence of open orbit in the definitions, but actually in this setting, that finiteness of the orbit, it's apparently a stronger conditions, but in this setting it is equivalent. And also in the real setting it is equivalent. So this is another remark. And also there's a notions due to Silberg, weakly symmetric space. So in this case, H is compact. And Akihisa and Wimberg prove that Z mod H is weakly symmetric space for compact H if and only if its compressification is spherical. So this is explanations of the notions of the spherical and real spherical. Okay, now analytic viewpoint of spherical space is the following. So this is first proved by myself and Oshima. That we want to study analysis on homogeneous space X equals Z mod H beyond the symmetric space case. And then the main important thing is that whether or not the function space is under good control of the representation theory or not. And transitivity of the G on X is not enough. And so we need some further conditions to have a good control of function space. And one of the formulations of good control is that each irreducible representation of Z appears in this space with a fixed number, at most fixed number of times. So namely, multiplicity of each representation has a uniformly bounded properties. And this is true for symmetric space, but the theorem says that such a thing happens exactly when its compressification is spherical. So we note that this analysis is real object, but classification conditions of uniformly boundedness is characterized only in terms of sphericities. And here, for later purpose, I only write reductive subgroups, but such a theorem is true also for non-reductive case. But in that case, we need to consider line bundles as well. Okay, and also there's known connections of algebras and geometry previously. So, for example, so that this ring is a ring of G-invariant differential operator on X. Then commutativity of this ring is equivalent to sphericity. More strongly, that this is a polynomial ring. So this is an extension of the Hashchandras isomorphism. So all of them are equivalent, and this is due to Knopf. And what we did is that equivalence of these geometric conditions on the analytic conditions. Okay. And we use this result for the branching problem. And then we have to be careful about the topology for the restrictions, but the following theorem holds. So namely, we consider uniformly bounded conditions of the restrictions from the representation of the large group Z to a smaller reductive subgroup Z prime, not necessarily compact. And the conditions is that pi is arbitrary of the representation of Z, and small pi is arbitrary reduced representations of the smaller group Z prime. And the uniformly bounded multiplicity result conditions is equivalent to that this homogeneous space is spherical. Namely, as a manifold, this is a group manifold GC itself. But with the action, we consider the action of the direct product group GC times GC prime. So namely, GC acts from the left and GC prime acts from the right. So these two conditions are equivalent. And then again, that we emphasize that the first conditions is defined for the real forms, but the second conditions depends only on complexifications. And then this conditions is actually studied earlier when G is compact, and also studied earlier the connections of rings. For example, the ring of invariant enveloping algebra, which is invariant by Z prime under the adjoint action is commutative or equivalently to a polynomial ring. These are studied earlier. And in the case G equals Z prime, then of course this restriction is trivial questions. And then this ring is center of the enveloping algebra, and so this is polynomial ring by the high-Chandler isomorphism. And in the case G and Z prime is compact, then such questions already appeared in the representation theory, but for finite dimension representations of compact groups. And then Constant and Kremers classified independently in the 70s when this happens. And actually, essentially, this happens when its complexifications is GLN minus 1 or SON, ON minus 1 up to outer automorphisms. And so this also appears, for example, Gang gross plus conjecture, their real forms. And moreover, that so this previous case that this upper limit is not necessarily 1. In many cases, this is some larger numbers than 1. But for the restriction case, that in many cases this is 1. And this is proved by Sun and Tu. But we also note that even if G and Z prime is connected, but this number is not necessarily 1. In some cases it is more than 1. But in most of the cases, this is 1. So this is proved by Sun and Tu. So this is again equivalence of representative theoretic property and geometric properties, and also previous known connection with the structure of the rings. Okay, and similarly for but this is a stronger condition, so uniformly boundedness. And now we want to consider weaker assumptions, namely try to capture broader setting that like high-Chandler's admissibility theorem says that his theorem does not say uniformly bounded, but individually finite. So we also are interested in the case individual finiteness conditions. So this is the conditions, namely multiplicity is finite individually for any irreducible representation of large groups and any irreducible representation of smaller groups. So this is the conditions of the pair Z and Z prime, pair of the reductive groups. And this is characterized by the geometry. And now real geometry. So previously characterized by complex geometry, but now characterized by real geometries. Namely, this space is real spherical. And as we saw that in the case G prime K, then this condition is satisfied. And this is satisfied because of the Gauss-Iwasawa decomposition says that this is a real spherical. And then in this case, the assumption condition says that this is High-Chandler's admissibility statement. And but this is not a tautology. We use this for the in the definitions. We use K admissibilities. But actually, the proof from here to here, in this case, says that if representations is irreducible and has infinitesimal characters, then each K types appears with finite multiplicities. So there are non-equivalence conditions of admissible representations. And one of the equivalence is included in the proof of this, where we use not algebraic techniques, but we use system of partial differential equations and construct some compactifications of the manifold, and then all informations transferred to the geometry of the manifold. So this is our approach, and which is applicable also to the restriction problems. And we note that even if G and G prime is a reductive symmetric pair, this condition is not necessarily satisfied. If G prime is compact, this is satisfied, but for arbitrary reductive symmetric pair, this condition is not satisfied. And complete classifications of reductive symmetric pairs satisfying these conditions, so equivalent to these conditions, was accomplished in a paper with Matsuki and in Dinkin's birthday volume. And I noticed that Dinkin and High-Chandler's is almost the same age. The birth year is 1 year different. Okay. And so here's some test case. So this is an irreducible symmetric pairs, and in the looking at the classification, Belgius infinitesimal classifications of irreducible symmetric pair, this type has the most parameters, four independent parameters. So it's a good test case in what cases some conditions are satisfied or not. And then for the uniformly bounded conditions, if we apply theorem 3, and this means that either this part is 1 or this part is 1. So this is exactly the case of the local gross plus conjectures case. And then in this particular case, that these conditions implies that multiplicity is 1 by Sun and Chu. And so actually these three conditions in this case are equivalent. And the finite multiplicity case includes, of course, this case and also High-Chandler case, namely G prime is compact, but also some other cases like P equal 1 or Q equal 1. And this is exactly precisely the classifications of finite multiplicity property, that individually taking any representation multiplicity is finite. So we see that not all cases multiplicity is finite. So we ask ourselves the following questions. So back to the setting that G and G prime, suppose that this is a reductive symmetric pair, like as we saw that this pair GLN to ON or OPQ to OP times OQ, but it's a non-compact setting. Then we have many parameters. Then as we saw that it may happen that multiplicity is infinite, even if we take reduced representations in both cases, and even though this subgroup is maximal subgroup of Z, but still multiplicity may be infinite. So we may ask that even for such a cases, we ask that if we take some specific representation pi, then multiplicity is finite or not. Or more precisely, that we ask the following questions. Does there exist at least one infinite dimensional representation pi of the larger group Z, such that the following bounded multiplicity property holds, where pi runs over all representations of smaller groups? The answer is yes. So for simplicity, that let Z be a simply connected non-compact semi-simple Lie groups, And then there always exists infinite dimensional irreducible representation pi of Z such that, and also there exists some constant C such that multiplicity is uniformly bounded for all the irreducible representations of the subgroups and all possible reductive symmetric pairs G and G prime. So there are such infinite dimensional representations. So we know that even for G prime's case, that High-Chandler admissive theorem says guarantees only individual finiteness. But the condition here is that uniform boundedness. And so we need to take specific representations. And special case is the tensor product case that also we can find a pair of irreducible infinite dimensional representations pi and pi 2 such that tensor product is uniformly bounded properties. And this theorem is not an existence theorem, but actually the proof provides a concrete information about which representations has such a bounded multiplicity properties. And then, of course, extremal case that if there exists minimal representations, so many cases it is the case. Or a little bit more generally, that if the associated varieties of pi is the closure of the minimal nilpotent orbit, and then we have a bounded multiplicity properties for all reductive symmetric pairs. And so at this moment, I'd like to give some method of the proof. For the extensions of High-Chandler's admissive theorems, namely without continuous spectrum and finite multiplicity, that the first approach of my first approach was to use micro-local analysis. So consider the hyperfunction characters for the restrictions and then give some estimate of the singularity spectrum by using several complex values argument. And later, an alternative proof that I gave is more elementary, that use some abbreviations of the representations, so using associated varieties and some argument of symplectic geometries. And concerning, so this is for discrete decomposable case. And then approach for the uniform bounded or finiteness criterion for the function space or the branching problem. The first was by joint work with Oshima that we use, as we mentioned, that use some captures such a multiplicities by means of the system of partial differential equations. And then we construct some compactifications and then look at the boundary data, hyperfunctions boundaries, and then information is captured together with the geometry of the boundaries. And this gives a one direction upper estimate, some explicit upper estimate of the multiplicities. And then the lower bound that we construct a kind of the integral transform to construct such an intertwining operators. And then the constructions of the integral transform uses some geometry of the boundary data, and this gives some opposite directions. And then some other methods for the that later extended by my students, Tauchi, Kitagawa, and so on, and also some individual, not a uniformly boundedness, but individual boundedness by Eisenbart and Gorevich uses again differential equations, holonomic D modules, and also by myself. And then also some individual family of representations, sometimes some notions of the visible actions on complex manifold, similarly co-specific actions on symplectic manifold helps us to give an upper estimate of the uniformly bounded multiplicities. This we employ such a method for the theorems. So this is some result of the boundless multiplicities and finite multiplicities that we have considered some extremal cases. Namely, we consider all uniformity for all irreducible representations or specific representations. But now we consider in a more refinement of the results in the following setting. So we want to understand the uniformity of the multiplicities not only for the representations of smaller groups, but also with respect to the representation of the larger group, but not all representations. But we want to find a family, specific family of kind of small representation pi of irreducible representations that I write symbolically omega. So this is a family of representations of the large representations. And then we want to find the following. Given a pair of G and Z prime, G prime is reductive subgroup, not compact, and try to find a family of representation that still uniformly bounded multiplicity property holds, where representation of larger groups runs over all this specific family omega, and small representations runs over all representations, because we want to understand branching problem, so we want to consider all representation pi. Then theorem 3 in this context, theorem 3 discussed necessary and sufficient conditions in the case omega itself is a set of all irreducible representations. Then we find that only very special case where G and Z prime is GLN minus 1 or ON minus 1, and its real forms. And on the other hand, the theorem 6 says that we take arbitrary pair of reductive groups, reductive symmetric pairs. Then we saw that if there exist minimal representations, then it's a singletons. Then we have such an estimate. So now we want to consider intermediate case, not a singletons, not whole things, but now we focus on the case H distinct representations that we recall the definitions. So let H be another closed subgroup of Z, and then we say that irreducible representations is H distinct representations if distribution representations has a non-trivial H fixed vectors, or equivalently by the Frobenius reciprocity that pi shows up in the space of the functions on Z mod H. And we collect all H distinguished irreducible admissible representations denoted by IRZH. So this is a subset of IRH. Then what we want to understand is that starting from H and then induce up Z, so namely consider H distinguished representations, or equivalently representation of Z that appears in the space of functions on Z mod H, and then restrict to the subgroup Z prime. So we are considering the triple. And then we want to consider the branching problem of the representations appear in that way. And then if we have a good control of the restriction or not by means of the bounded multiplicity properties. And then naive thought is that if the subgroup H is large in some sense in G, and then we expect that H distinct representations may be small representations in some sense. And also, if the representation Z prime, if the subgroup Z prime is large in some sense, large subgroup in some sense, and if the representation is small in some sense, then we may expect that the restriction is of this representation to Z prime is under good control. Say, have bounded multiplicity properties. Then how can we measure largeness? For example, rank or of Z mod H may be properties. But we don't consider in that way, but we try to formulate as a property of the triple. not individually. So what we want to understand is that try to find the criterion of the triple such that this uniformly bounded multiplicities holds for all irreducible representations appearing in the function space on Z mod H, namely H distinct representations, restricting to Z prime. And we give a complete answer when Z and H are symmetric pair. Z prime is not necessarily symmetric, as follows. So we need some terminologies. So let Z mod H be a reductive symmetric space, namely there is an involutive automorphism sigma of Z, and H is an open subgroup of the fixed point of sigma of Z. And then we consider its complexifications, and then take a compatible maximal compact subgroup, namely its intersections of all the other reductive groups to give us a maximal compact subgroups. Then we define relative Borel subalgebra for Z mod H and relative parabolic subalgebra for Z mod H. And the relative Borel subalgebra denoted by B, Z mod H, for symmetric space Z mod H, is the parabolic subalgebra or complex parabolic subalgebra in GC, defined by a generic element in the space of -1 eigenvalue of the differential of sigma, or its conjugate. And a relative minimal parabolic subalgebra denoted by P Z mod H for reductive symmetric space is a real parabolic subalgebra defined by a generic element of the hyperbolic element, which is a -1 eigenspace of sigma, or its conjugate. And this is uniquely defined up to conjugations. And we note that the relative Borel subalgebra is not necessarily solvable, in contrast to the group manifold case. And also this relative Borel subalgebra is determined only by the complexified symmetric algebras, symmetric pairs. So this is the remark. Then here's bounded multiplicity criterions. So suppose that Z and H are real reductive symmetric pair, and Z prime is just a reductive subgroup, not necessarily symmetric pairs. And then we want to restrict starting from H and induce up to Z, and then restrict to Z prime. And then ask uniform bounded multiplicity properties. And then uniformly bounded multiplicity holds for this triple. So this, in our terminology, this is a bounded multiplicity triple. If and only if this space, this partial Frag varieties, GC mod this relative Borel subgroups is GC prime spherical. And then we can give a complete list of the triple for this. And also similar results for individual finite multiplicity criterions, but maybe I skip this because later argument I only use bounded multiplicity triples. And then the proof already I have explained that essentially we use differential equations and the D-module argument, but in addition that we again encounter with earlier pioneering work of High-Chandler's. Namely, we use some extensions of High-Chandler's subquotient theorem. That, as in the yesterday's explanations of sources, that any irreducible admissible representations can be realized in the subquotient of principal series representations. But if the representations has more properties like H distinguished representations, then we can use some. We can get further conditions of these inductions. And actually, any we can use instead of the minimal parabolic subgroups, but we can use relative minimal parabolic subgroups, and then induce from finite dimensional representations. And this V is a finite dimensional representations then it's actually that's not a subquotient theorem, but actually a quotient theorem like a Kasselman's embedding theorem. That any H distinct representations can be obtained as a quotient of some induced representations that not necessarily minimal public, but V. But also, more important thing is that V is not arbitrary, but we can also control which V appears here. And which V appears, V is exactly controlled by relative Borel subalgebras. And so this is an additional lemmas for the proof of the previous theorems. Okay, so I just give a comment that previous in the theorem 3 that we give an earlier work that when uniformly bounded multiplicity holds where representations are arbitrary for larger groups and smaller groups. But this theorem is recovered as a special case of this newer cases because we consider this particular case. Group manifold case, group manifold is considered as a special case of the symmetric pairs. And then if we apply theorem 7, the previous ones, and then this theorem is a special case of this one. And more interesting case like here that we consider reductive symmetric pair. And previous that we needed some constraints of this 4 parameters. But now we consider P1, P2, Q1, Q2 are arbitrary. So this is G and G prime. So we want to restrict from these groups, restrict to these complicated subgroups. So this is the symmetric pairs. But if we consider H distinguished vector where H is this one, then the previous theorem, theorem 7 says that we have a uniformly bounded multiplicity whatever P1, PQ, P1, Q1, P2, Q2 are. For any 4 parameters, this is uniformly bounded. And this is one example of the uniformly bounded triples, bounded multiplicity triples. But actually, we can give classifications of the triple of H, G, G prime with these properties. Okay, so this is what we have so far explained about restrictions of H distinguished. So far, these 3 topics are representation theory, so restriction from Z to Z prime. And then we want to find nice properties inspired by the earlier pioneering work of Haish-Chandras in different directions. Okay, now I want to change a topic that think about spectral analysis on Z mod, H mod, gamma. And that we give just some ideas that we want to apply this result of branching problems to the spectral analysis of a local symmetric space, where gamma is a discrete subgroup Z acting properly discontinuously on Z mod H beyond the Riemannian setting. So namely, this is a pseudo-Riemannian symmetric space. And then usually, gamma is much smaller than the lattice. And then our idea is to use the Zariski closures of the discrete groups and then use a branching law from representation Z to the Zariski closure as a method of this problem. But let me explain what we want to do. So this is a figure is a classical setting. So we consider Lie groups and closed subgroups and discrete subgroups acting properly discontinuously on Z mod H. Then we want to understand gamma periodic eigenfunctions or distributions of eigenvalues and also expansions of arbitrary functions by means of the eigenfunctions, periodic eigenfunctions. And then already special cases are rich and deep. For example, in the case gamma is trivial, so namely in this case, for example, expansions of arbitrary function into eigenfunctions is partial type theorem. And if this is a group manifold case, then there's a pioneering work of the Gelfand, and then seminal work of the High-Chandler partial formula for the group manifold, and then extended to the symmetric cases. And so this is when gamma is trivial case, and when H is compact and gamma is arithmetic, and then gamma periodic eigenfunctions is closely connected with the local series of automorphic forms. And even in the case G is abelian, and then H is trivial, and gamma is just a lattice, then we think of the eigenvalues of the Laplacians, which is normal elliptic but indefinite Laplacians. Then eigenvalues is exactly the same with the values of indefinite quadratic form at the lattice point. And then famous Oppenheim conjectures, which was originally studied by analytic number theory, but then settled by different method, namely by ergodic theory by Dani and Margulis. So this is a case of the indefinite metric case, and but these are variants. But my long project is try to generalize this for non-trivial gamma and non-abelian G and non-compact H. And then new further difficulty arises first, that if we have a nice gamma or not. So this is the geometric questions. This is related to the one of the central problem in geometry, that how local geometric structures affects the global nature of the manifold. This has been studied a lot in the Riemannian setting, but not much known for non-Riemannian setting. And we are now thinking of the local homogeneous structures. In that case, the global structures is controlled by the discontinuous group acting properly discontinuously. But the existence of such a discontinuous group is non-trivial questions. And then for analytic questions, that, for example, Laplacians in the non-Schur Riemannian case is normal elliptic. So it's not obvious that whether Laplacian has a self-adjoint extensions or not. So namely that it's not obvious that arbitrary functions is decomposed into the eigen spaces or not. Even such a basic questions is non-trivial. And from representative theoretic viewpoint, if H is non-compact, then then always G mod gamma, the volume of the G mod gamma is infinite if gamma acts properly discontinuously. So this means that the regular representation on G mod gamma is not well controlled. So this is another difficulties arising from these stations. Then we need a new method to attack these questions, and the method I'm using is branching program from Z to the Zariski closures of these gammas. And actually that we shall use two topics that I have explained. That one is, of course, we have to use some global analysis of G mod H in terms of representation theory of Z. But also, we use some representation theory of Z prime on Z prime spherical spaces, and then restrictions from Z to Z prime. So this is a new ingredient that we attack these questions. And so I just give a terminologies of this. So first, geometric questions. As I mentioned, that it's not easy to find such a proper discontinuous groups because if H is compact, any discrete group acts properly discontinuously. But if H is non-compact, then any lattice cannot act properly discontinuously. No lattice can act properly discontinuously. So gamma must be somewhat small. And then for this, we take the following strategy. First, consider continuous analog of the problems. first find a reductive group Z prime acting properly. So this is a continuous analog. And we can give a precise, computable necessary and sufficient conditions for this. And then we take a discrete subgroup gamma of Z prime. Then it automatically acts properly discontinuously if gamma sits in Z prime. And we call that the quotient is standard quotient of gamma. Then here's a theorem. In preprint is Fanny Cassel. That let Z mod H is a reductive symmetric space. And then this is a High-Chandler isomorphism, and we consider joint eigenfunctions of the invariant differential operators. And suppose that another reductive subgroup Z prime acts properly on symmetric space, on Z mod H, and also acts spherically. In such a case, we take arbitrary discrete subgroup gamma of Z prime. Then we get a standard quotient. Then the theorem is that actually Laplacian has a self-adjoint extensions, so essentially self-adjoint. This is a part of this theorem, that any arbitrary functions can be expanded into joint eigenfunctions in these situations. And so this is an inversion formulas and the Plancher type theorem. So this is a family of the measurable family from this to the space of eigenfunctions. And how the previous topics and this topic is connected, the idea is the following. That under the same geometric assumptions that any H-distinguished representations is admissible to Z prime. So this is the theorem. So this is in these situations inducing and restriction, then no H-distinguished representations has no continuous spectrum for Z prime. But moreover, the restrictions push is uniformly bounded. So this is a key lemma for the proof. And the previous theorem 1 gives some admissible criterions formed purely by representation theory. But this theorem is, the proof uses some geometric argument. And also this is comparisons of our uniformly boundedness theorem for the H-distinguished representations restrict to Z prime in terms of sphericity. But in this case, the restrictions may have a continuous spectrum. And our setting is a little bit stronger that no continuous spectrum appears, but uniformly boundedness. And this is exactly that we are working on the locally quotient space, locally should Riemannian symmetric space. And here are some typical, so there are other examples, but these three examples are particularly interesting from geometric viewpoint. And the first example is due to Kulkarni, who was a director of this High-Chandler Institute some years ago. He worked on the geometric side of this anti-de Sitter space by using the lattice of Z prime UN1. And in this case, that H-distinguished vectors of SO2N2 restrict to UN1 does not have any continuous spectrum and uniformly bounded. And some other interesting geometry is the indefinite Kähler manifolds and also 15-dimensional space form, so constant curvature space of signature H7. And in this case, we take a lattice of spin 7, 8. In all cases, any H-distinguished representations of Z decompose discretely to the Zariski closures of the discontinuous group Z prime, and each multiplicity is uniformly bounded. So this is a geometric setting of the ones. So this is the last slide. What we are looking is that to find a non-trivial example of geometry, we use a continuous analog. So we first find a reductive subgroup acting properly. So G itself cannot act properly because this is a non-Riemannian setting. Then we take arbitrary lattice gamma in Z prime. Then the second one is the most non-trivial part, that we want to expand by means of the eigenfunctions of invariant differential operators by High-Chandler homomorphism. So this ring of the invariant differential operators acts as a scalar on each eigenspaces. But very important thing is that we consider much larger algebra, which is just G prime invariant, namely invariant by gamma. Then, under the assumption that GC prime acts spherically and G acts properly, then there's a hidden symmetry. So, namely, this larger algebra acts on this space. And this algebra controls the representation of the Z. And this algebra controls the representation of the smaller group Z prime. Here, the branching law comes in. And so we go on opposite directions, and then this information gives a spectral analysis on the G mod H mod gammas. So this is the end of the talk. So I have explained some topics inspired by High-Chandler's admissibility theorem, and then discussed its applications to the spectral analysis of the pseudo-Riemannian locally homogeneous spaces. Okay, thank you very much for your patience.
So, any questions?
So now you have dgx is commutative, but if
so
looking at the dgx, the ring of invariant, that's commutative.
G mod H.
Yeah, for the reductive symmetric space. Yes. But now you don't necessarily have elliptic operators there, right?
No.
So what can you say about the wavefront set of a joint eigen distribution?
Wavefront set of joint eigen. Usually that joint eigen functions are not necessarily analytic functions.
Yeah,
so
that's what I'm saying. So does it have mild singularity? Can you say something about the wavefront set, or even the singular support?
So for G mod H or G mod H mod gamma?
G mod H.
Okay.
Not gamma.
Okay. So but you are considering operators or all eigenfunctions. So you can consider two questions. One is that just consider some second order operators, but also can consider higher order operators.
Yeah. No, so but here the Casimir go into a hyperbolic operator.
Yes.
Yeah, so it's no longer
right.
It's a wave function equation now. So
yeah,
and I'm saying, so in general, can one say anything about the singularity of this distribution? Now there is not a smooth function.
So I want to questions. So so we can say some general things that comes from general differential operators, but I don't have concrete answer for this particular.
No, I was asking this because the theory of spherical functions for G mod K is very rich. So here, what is the analog here now that the eigen distributions?
Okay. So yes. Yeah, so then there's a lot of interesting things, but not directly related to your questions, but there's one interesting thing that, for example, that thinking of the characters,
Yeah.
that, for example, Harishchandra's another theorem that characters of the reduced representations is locally integral functions on Z. But if we consider, related to your question, that invariant so spherical functions on Z mod H, and then similarly to the H, left H invariant, and then such a distribution is no more, not necessarily locally integral. So there are such examples already.
Thank you very much.
Any other questions? So if there are no further questions, let's again thank the speaker. And
thank you very much.
we meet again at 11.